Hi, good day. I'm here to present on the segmentation in 8086 architecture. Recollecting from the 8086 architecture, we remember that it has 20-bit address bus, but practically speaking, it has only 16-bit address bus and 16-bit data bus. But we can actually point to a 20-bit address location. How is that actually possible with a 16-bit address? Is that is through this concept of what is called as memory segmentation. Okay, this memory segmentation in 8086 expands the scope of 16-bit address bus to point to a 20-bit address location. Okay, so we'll see how it is being. So this address bus is actually pointing to 2 power 16 address lines, practically speaking. Okay, so if I need to put my 1 MB of memory that is available in as per the concept here. So if I put it as a linear addressing, I can point to any locations in the memory here, basically. But if I segment my memory and I define my memory locations with respect to code segment, data segment, stack segment, and extra segment, I can make use of 1 MB memory locations conveniently in the program as per my requirement. Let's say it is respective to that particular user who is going to program that particular hardware to define which is his particular memory location starting from. There is no defined memory location that we are going to start from here. For example, in this particular scenario, the data segment is starting from 2000 memory location. And only proposal that they have put forth here is that any memory address location we can point maximum to 64 KB address locations. Okay, and then I have defined my 2000 as the base address location for this particular data segment. And similarly, here it is wrongly mentioned. It is 3000 as the base address location. And for stack segment, I'm starting from 5000. And for extra segment, I'm starting from 7000 as my memory location that I'm starting from each other. This is again just the base address starting point. And we call this as an offset. How to calculate this offset, we'll discuss in the next slide. And this is the maximum memory locations that I can point to each of the segments here. So how do I point to 1 MB of memory location? I have segmented my memory now, but I also bring in the concept of offsetting. This is available as part of the architecture in 8086. We call this as a real mode architecture, memory segmentation here. So in 83, 86, there is private mode, few other modes available. Since we are focusing only on 80, 86, let's talk about real mode memory segmentations here. So what we should define here in real mode addressing is that we need to define what is the segment address and what is the offset address. So by this, we can actually point to a defined base address and then respective offset address to calculate the physical address location. Let's see that how it is being done. So we see here my segment address. It can be code segment, data segment, stack segment, or extra segment. Is a 16-bit address as mentioned over here. Okay, and what we do is that we left shift this particular 16-bit and add 4 more zeros and make this as a 20-bit address location. Okay, and we also have the offset address defined, and this particular offset address is a 16-bit address location. So we add these two address offset as well as the segment address to prepare the physical address, which is a 20-bit physical address. That is what is being illustrated here. Okay, I'll again repeat, we have a segment register, we left shift it, add 4 zeros, and then we offset add this with that offset 16-bit address, and then this will give the real physical 20-bit address location actually. example how this is being done. For example, if I have 74A2H as the data segment base address, and then the offset address is given as 438E. So how do we calculate the physical address is that we left shift. This is a hexadecimal left shifting, so we add only 10 there. So well, while left shifting, we get it as 74A20, and then offset address is 4380. When we hexadecimal add over this thing, we result in 83DAE. So the concept here is that we define the lowest physical range here as 74820 as per this particular definition. And maximum memory location that it can point is 64 KB. In hexadecimal, it is double F double F. So if we add double F double F to this 74820, it points to 8FJ1F, that is pointing to this particular maximum upper data segment range here. And then the actual physical address is pointed to this particular. In a way, it is like offset is nothing but displacement from the base address. So this is the physical address location. Okay. In microcontroller, we can refer this physical address location by this physical address, sorry, microprocessor. We can refer to this physical address location as 83DAE, or we can also refer this particular physical address as a logical address by this particular concept. 74A2 is to 4380. 74A2 is the base data segment address. 4380 is the offset address that we have defined. So this logical address, this physical address is same. Okay, except that the way we represent is going to be little different. We'll say this again with one more example. I've defined my base address as A4FB and then my offset address as 4872. So this is the logical address. I'm asking to prepare the calculate the physical address location. So what naturally what we got to do is left shift this A4FB. So I'm adding four binary zeros here. So I'm making it as a 20-bit address. And then I'm adding the 4872, which is the offset address. So finally adding it, I'll result in A9822, which is the real physical address for this particular logical address. Okay. So one more thing to remember here is that when we work with segment registers, we define the respective offset registers also that we work with. With respect to code segment, I prefer to use instruction pointer. When I'm defining the stack segment, I prefer to work with base or stack pointer. When I work with the data segment, I prefer to work with the source index register. And when I prefer to work with the extra segment, I prefer to use the destination index or DI register here. Now let's check this with a couple of other examples. So I define my code segment with this 0400. So which means that when I the base address of this particular code segment, I need to add one more zero here. So which means it will come to 4000H. And then when I'm working with code segment, as per my index register would be instruction pointer, which is going to be 0056. So what I need to do is that add 56 with this 4000, so which will result in 4056. So my 4056 is the real physical address here. Okay, which the calculation is done over here as shown. Or the logical address would be 4000 is to 56 is the logical address that would be resulted. The next one more example here. I define a data segment. I have my base address defined in this data segment as 05C0. So I add one more 0 bit, so which makes it 5C00. And my offset address here is going to be 50. Since I'm using the DS segment register, I use the EA index register here. So I offset it by 50. And then, so my physical address is going to be 05 sorry, 05C50 is the physical address, actual physical address. If I have to put it in logical address format, it can be 05C50 is the logical address for this particular, which is equivalent to this 05C50H. Okay. And then with respect to stack segment, if I'm going to work along, my base address I've defined over here, and then my offset address is also defined as 100. So my actual physical address is computed as 0A100H. So that is the real physical address. If I have to put what is the logical address for this, it is going to be 0A00 is to 100. So that is the actual physical address location. Remember, stack makes use of the push and pop operation, which is very much significant for any stack operations that we are going to carry out. So we'll move into understanding what are the different types of segmentation that we have. In 1886, we can work with overlapping segmentation and non-overlapping segmentation. Overlapping segmentation means what is given over here. Here, if I define a segment to be 64 KB in size, but what if my program code segment wouldn't require that much amount of size? My code segment is only, let's say, using only 100 KB of, 10 KB of memory. So the rest 54 KB is going to be left unused. So what I can define is that I can define my code segment to be only 10 KB. And then I can make use of that the next 54 KB onwards, so that I can use that effectively. So if I keep the rest 54 KB unused, my memory is going to be unused here. Okay, so that is why this overlapping segmentation gives me an advantage of using the segment that was unused previously while defined before to be reallocated to the next segment that we are going to use. However, please understand, one segment can be maximum defined for 64 KB only. So that is something that we should remember. So like this, if you can see over here, we have a first segment defined, and then second segment, it is understood that first segment is going to use only this set of locations here. Okay, so, so this space is left free as per that particular logic. So I'm making use of this particular space for the second segment allocation here. Similarly, again, if second segment is not going to be used, I can define third segment. So I can nest it on. Okay, n number of segments I am trying to define over here. Okay, but the regular design, if I am using a non-overlapped segment, I can maximum define 64 KB each locations, and the maximum 16 such 64 KB locations can be allocated. So which is going to maximum of 1 MB of memory locations that I can refer to. So why do we need segmentation? What is so significant about this particular segmentation is that it provides me a powerful memory management mechanism. When we are working with microprocessor, when we are going to write big code at future point of a time, managing memory is going to be a very significant scenario. How do we manage this? Memory segmentation gives me that advantage of using the unused segment of memory effectively. And any data related or stack related operations we can perform in a different segments. So which means that it provides, instead of linear addressing, I can define my segments for respective segment of code or data or stack operations here. Any code related operations can also be done in separate code segments. So we can, even if I have my sub function, I can define one other segment of memory as a code segment. I can start defining that particular segment as to be used. And it also helps when easily processing to share the data between the segments. Okay, and please understand, without segmentation, if it is only 2 power 16 locations of memory, it doesn't point to 1 MB of memory location. So this also helps me in 1 MB of memory location to be addressed using this particular segmentation. So And finally, it is also possible to enhance the memory size of the code data or stack segments beyond 64 KB by allotting one more extra segment to this particular. But there is a constraint at any point of a time we can work only with 4 segment of memory. Okay, one program when we start writing at any point of a time we can only refer to only 4 segment of memory location. So with that particular introduction, I'll try to show a demo. So this demo, what I'm trying to provide here is actually, so I'll write an assembly program to write first 10 odd numbers into a data segment. Okay. I'm defining my data segment. My data segment is starting from this particular memory location 2000 here. Okay, and then my the data I wanted to show is 0, 1, and then for each incremental locations of 1, 2, 3 for those address locations, I want to increase my I want to put my next odd number. So in a way, I want to put 10 odd numbers into this particular locations. So I define my data segment and I define my offset over here. So I'll write an assembly program for this thing. So first what I do here is that I define my data segment as 200. So what I need to do is that I to put it to accumulator actually, and only through accumulator you can move that to the data segment register, DS register. Next, I am working with a data segment, so I'm making use of the source index register here. So I initialize my source index register with this, 4 zeros here. And then next, what I'm doing is that I'm defining the first odd number. One is the first odd number, so I'm defining the odd number to the accumulator. And I want 10 odd numbers to be updated into the memory segment. So I define my 0A as the counter value. Okay, remember CL register is an 8-bit register which can be used for any counting operations or loop operations. And then I define a label called ABC, and then whatever the value that is in the accumulator, I am moving into this particular data segment. Okay, when I'm pointing within this bracket of SI, so SI is computed by this particular process, logical address calculation, sorry, the physical address calculation. Okay, so data segment is 200. So while left shifting, it will move to 2000. My offset is 0, so which means 2000 is the address location. So my one odd number is stored at that particular location. Next, what happens? We are increasing the index for this thing. So the next address location is pointed out here. Then I'm adding 2 to this accumulator. Why is that? Is that I want to move to the next odd number. Next to odd number next to 1 is going to be 3. So I'm moving to the incrementing it by 2. And then I'm looping this. So this loop will run 10 times actually. After executing 10 times, this counter value will get to 0. Once it is getting to 0, this program will be halted. That's it. It will not run any further. Okay. I'll try to show this particular demo in the EMU emulator here. Okay. So I've written the same program here. Um, Let me compile the program. I'll also open the memory segments to show how it is being represented. And remember, as per the program, I wanted to move to this particular 2000 memory location, right? So the logical address is being defined here. Okay, so 0 to 100 with an off shift of 0000. Okay, right now no values are there. Okay, the same program I'm running. Let me run this program. The program run is completed. You can see it got updated with all the 10 odd numbers that we wanted to store to this particular data segment here as per the program. Okay, remember my code segment, I have written it into the 1000 memory location by default. That is how the simulator runs actually. Okay, so I hope this particular program should have given you a brief idea about how this memory segmentation is being implemented in this particular 8086. Okay, any queries you can reach.